going to talk about electrolyte effects again. Previously, we discussed about the common ion effect. Okay, so what common ion effect is all about? That the previous problem we answered earlier. Common ion effect decreases the solubility of your precipitate or your sparingly soluble substances or whatever substances it is. It decreases its solubility because you added common ions. Okay, so it's pretty obvious, of course, because looking at the ice table, you will observe that adding common ions will directly affect your ice table. Okay, so the next question there is that what if I added ions or molecules that are not in the equilibrium system? For example, I added silver, not silver. For example, I added sodium sulfate. Would there be an effect in the equilibrium system? We don't know because there is no sodium ions in the ice table nor sulfate ions. So that means, what's the effect? Okay, we don't know yet. Okay, so in reality, that puzzled the scientists before. Okay, so let's look at this publication by Stulzberg, okay, in 1999. Um, what you can observe is that we have this equilibrium system. Iron 3 ion and thiocyanate ion. This is an equilibrium with iron 3 thiocyanate ion complex. That's color red. Okay. Okay, so this is the reaction quotient or the concentration of the product over the reactant. So in this y-axis we have the reaction quotient. On the x-axis we have the number of molarity or the molarity of the potassium nitrate. So as you can see, do you think potassium nitrate has an effect with the equilibrium constant? Okay, so obviously it doesn't have any, but looking at this experiment, as you can see, the reaction quotient decreases as you increase the let's say diverse ions. Diverse ions are ions that are not in the equilibrium system, because we cannot see potassium ions here nor nitrate ions here. That means when we added diverse ions, the equilibrium constant or the reaction quotient is still affected. Okay, but why? Okay, we still don't know yet the answer. Okay, so that's the first idea. Okay, so the idea that we can get here is that when you add inert salts, it shifts the equilibrium despite that it is not a part of the equation. There's no potassium here, there's no nitrate ions here. However, it still affected the equilibrium constant or the reaction quotient. Okay. Okay, second observation is that this can be done in an experimental lab. However, due to COVID-19, we can't do that. Okay. So another observation is that when you dissolve calcium sulfate in a solution with inert salts such as potassium nitrate, the solubility of that substance increases. That means more and more of the calcium sulfate dissociates when you add inert salts. When I say inert salts, these are salts whose ions are not in the equilibrium equation. Okay, so there's no potassium here, there's no nitrate ions here, so potassium nitrate is an inert salt or a diverse ion. Okay, so that is one thing that puzzled our scientists before. Okay, so they want to know why and they came up with this answer. Okay, so let's explain this. Okay, so I prefer doing it in a blank paper. Okay, so this is the idea. Let's say we have calcium sulfate. Of course, calcium sulfate dissociates into calcium 2 plus ions and sulfate ions. Okay, let's visualize it as circles. For example, this is calcium 2 plus. This is sulfate ions. Okay, when you add common ion effects, what happen? Common ion rather. When you add common ions, what happens is that you are adding either calcium 2 plus ions or sulfate ions. Then what happens to them is that these will recombine. They will recombine together to form the precipitate. Okay, so that's the idea. The two will recombine because they have opposite charges. This is positively charged, this is negatively charged. I know that positive is attracted to negative, so they will combine to form the precipitate. Okay, so they will combine to form the precipitate. However, oh my god. Okay, so however, if we added diverse ions, for example, potassium nitrate. Okay, potassium nitrate dissociates into potassium and nitrate ions. Okay, so what is the effect of those ions? They act as shields. Okay, so let's visualize that. Okay, so anyway, for example, this black circle there is the what do you call that? Anyway, so I'm going to draw it anyway. Okay, so let's say this is the nitrate ion. This is the potassium ion that came from this, the diverse salt or the inert salt that we have. Okay, what happens is that instead of these two connecting to form the precipitate, diverse ions actually block them from recombining. So the idea is that instead of calcium being attracted with sulfate, the case is that calcium becomes more attracted with nitrate ions because nitrate ion floods the surroundings of calcium ion. Okay, so the presence of inert ions such as potassium nitrate floods the surrounding of your ions, let's say the calcium ions, that prevents them from combining with their original partners, let's say. Okay, so that's the idea. Same goes for sulfates. These potassium ions prevent sulfate from being attracted to calcium. Okay, what happens is that our potassium ions flood the surroundings of the sulfate ions, thus preventing them to combine. Okay, so that means for diverse ions, the presence of diverse ions prevents the recombination of our precipitates. Okay, so let me write that down for you to take down notes. Presence of diverse ions prevents the attraction of ions to form precipitate. Okay, so that's the idea. They prevent the original ions, the calcium and the sulfate ions, from recombining to form the precipitate. Okay, so Hence, we can explain it using this logic. Okay, so when I say ionic activity, this is the amount of um, inert ions. So let me write that down. Um, this refers to the amount of inert ions. Okay, so when we increase the amount of inert ions or the ionic activity, more ions diffuse into the ionic atmosphere. So what is the ionic atmosphere? Let's go back. The region at which your nitrate ions and potassium ions reside is what we call the ionic atmosphere. That is a region in which your ions will flood your um, insoluble ions. Okay, so that means if we have high ionic activity or high amount of inert ions, the more of these inert ions will diffuse into the ionic atmosphere. Thus, there will be a less net charge for each ions in the solution. That means that nitrate ions and potassium ions are shielding calcium and sulfate ions respectively to prevent them from recombining. Okay, so that's the idea. That means less attraction for spirulina soluble salts. That means calcium 2 plus will no longer be attracted with sulfate because of the presence of the diverse ions in here. Okay, so that's the idea. Okay, so since there is less attraction for our soluble salts, there will be less precipitate. Okay, so when you say less precipitates, this means that the solubility will increase. We call this phenomena the diverse ion effect. So this is the second phenomena other than the common ion effect. So previously, for common ion effect, the solubility decreases. For diverse ion effect, the solubility increases. Why? Because there are um, inert ions that are flooding the ionic atmosphere of your original substances, hence preventing them from re-attracting to form the precipitate. Okay. Okay, so that's the idea. So for diverse ion effects, inert ions or diverse ions uh, blocks formation of precipitate. Formation of precipitate, right now that's PPT. It blocks the formation of precipitate, hence increasing the solubility. Okay, so that's the idea. And here, so this is the summary of this topic. The greater the ionic strength of a solution, ionic strength refers to the amount of diverse ions. The more diverse ions you have in a solution, the higher the charge in the ionic atmosphere. That means the more of those diverse ions will flood the original ions you have. In this case, that's calcium and sulfate. Okay. Uh, that means lesser attraction for those original ions, hence lesser chances to form the precipitate, or in other terms, the solubility will increase. Okay, so let's have this graph. This is a published paper by Marzako in 1998. Okay, so as you can see here, we have here an equilibrium system of potassium hydrogen tartrate. This is dissociating into uh, hydrogen tartrate ion and potassium ion. Okay, so that's the idea. In KCl, okay, so this is KCl. This is the solubility of this substance. Okay, in the KCl solution, the more KCl you add, the solubility of potassium hydrogen tartrate decreases because of the common ion effect. Okay, common ion effect tells us that when you add common ions, the solubility decreases. So for KCl, the common ion is, of course, the potassium ion. We have potassium ion here. Okay, so how about magnesium sulfate and sodium chloride? How about the two? Okay, so you can see the solubility of potassium hydrogen tartrate increases in the presence of magnesium sulfate and sodium chloride. This is the uh, opposite of the common ion effect, and this is called the diverse ion effect. Okay, so this is the diverse ion effect. So you can see there are no magnesium ions in our equilibrium system, nor that of the sulfate ions, nor Na ions, nor Cl ions. Okay, so there are no Mg2 plus, no SO4 minus 2, no Na plus, and no Cl minus in this equilibrium system. Okay, so that means when you add those diverse ions, the solubility will really increase. That's the explanation given by the diverse ion effect. How about glucose? Why is the solubility not changing as you add glucose? This answer is no-brainer. Glucose is not an ion. So glucose is not an ion, hence there is no um, electrolyte effect because glucose is not an ion, hence no electrolyte effects will be happening. Okay. So that's a general idea. Later on, we will discuss further about the ionic strength whatsoever.